Let's use some of the models at cmosedu.com in these next examples. So let's go to cmosedu.com, click on LTspice there, the quick link, unzip the contents of LTspice CMOS. Note that if we were to go look at the videos here, the video that I'm making, the text describing these figures is in this PDF adjacent to the video name, which is what I'm making right now. So what I'm going to do is I'm going to take a look at this, and let's just take this zip file and pull it onto the desktop, unzip everything. Yes to all. Alright. So all literally hundreds and hundreds of examples for you to play around with. Okay. So now if I go over here and I look at the Spice net list, I'm going to right click on this one and copy. That was in the LTspice. Now I'm going to go over here and paste. And I'm going to rename this CMOS edu _video _4. Now, again, this is zipped up right here and placed at this location, CMOS edu _4 zip. Alright, so let's open that up. Actually, before we do that, let's take a look at this simple net list, or the simple schematic right here. I want to discuss a few things here. This is useful for why currents can be positive or negative. So one thing you need to remember, Spice defines positive current flow as from plus to minus. This is a 10 volt source. So that means there's 10 volts there, there'll be 10 volts through here, and 10 volts across here, and 10 volts across here. The current will be flowing like this. So the current in Vs is negative. Over here we have a dependent source. This is what's called an arbitrary voltage value that's taken and says, hey, generate a voltage which is equal to the current that flows in R1 or the current that flows in R2. Now, depending on how we have these two resistors put together, we can get different values of current. So if the resistor is connected so that this is effectively the positive side of the resistor and this is the minus sign, we'll get a different current than if this is the plus and this is the minus. And the way to look at that and tell is with the Spice net list. So if I look at the Spice net list here, I see that Vs is Vs, this node name, to ground, and it's 10 volts. R1 is from Vs to ground, and R2 is from ground to Vs. And so if I run the sim, knowing these two resistors are flipped when I put them in, if I run the sim, I get that the current through R1 is -1, the current through R1 is +1, the current through R2 is -1. Now if I go back and cut those two connections, and then I move this resistor so we can do a rotate, Control R, a couple of times, and then I reconnect it. If I look at the net list now, I see that my R1 and R2 are connected in the same direction, and so thus the currents flowing in each one will be the same. So I go over here, and I see now the current through R1 is 1, and the current through R2 is 1. Okay, so let's move on to we'll put this in that file. Nice thing to look at net lists to find out why your currents are positive or negative. And the other thing was, running the sim, note the current through IS is negative. So the current flowing in RS is negative one more time, because Spice defines positive current flow as from plus to minus, and the current's actually flowing like this. Okay, so let's go back over and open up the CMOS video 4 and take a look at, just run through the basic schematics here and discuss them. This is a basic voltage divider where I've labeled this node 1, this node 2, put a 1 volt here, and I've got 2 resistors. When I run a sim, my operating point analysis comes up and gives me my currents and my voltages. Very simple. This illustrates the dot OP. In this sim here, we're doing the same thing except we change resistor values. So V out, resistor values are the same, but V out is now, or node 2 is now labeled V out, and node 1 is labeled V in. And when we run, we get the same results. In this circuit, we're doing what's called a transfer function analysis, and this is useful when we have a large circuit with, we're trying to find the behavior of the circuit, what's the gain through it. We define our output port as V out in ground, and our input is V in, and then we determine the transfer function. Well, gee, what is the transfer function going to be here? See, 2K divided by 1K plus 2K, so V out over V in is 2/3, or 0.6667. So I run, and my transfer function is 0.667. The other thing is that I can get the input impedance and the output impedance of the circuit. The input impedance is 3K, the output impedance is 666 ohms. So the resistance I see looking in this way is 1K plus 2K, or 3K. The resistance I see looking back this way is 2K in parallel with 1K, or 666 ohms. Okay. And these are all in the PDF. This circuit here, what we've done, it's the exact same circuit we had before, except we inserted a 0-volt voltage source. And this is useful for measuring currents. We'll put these voltage sources in to measure the current flowing in the circuit. And so now we're saying our transfer function is I measure, the output is I measure the current through that voltage source. Notice this doesn't affect the circuit because it's 0 volts. There's no difference between this node here connected to ground and it connected to a 0-volt voltage source to ground. So let's see, when I run the circuit, if I put 1 volt here, the current that flows is going to be 1 over 3K, or 3 milliamps. So my transfer function is going to be 3 milliamps divided by 1, or 0.003. So let's run. And so there we see our transfer function, 0.0003, or 1 volt divided by 3K. And our input impedance is 3K. And our output is infinite because we've removed this voltage source, and so now our output impedance is an open looking back in to the terminal. Okay, again, use of the transfer function. Now take another one. Here's my ideal op amp. This is similar to what I did in the last lecture. Well, let's grab it. And you can see I've called it VNP and VNM and V out in this one. And instead of 1E6, I called it 1 meg. But you see here's an inverting amplifier, and our transfer function, V out in ground, and V in is going to give us a gain of -3. So when we run this, we get a gain of -3, and it's not exactly -3 because our op amp has finite gain. And so if we were to go and increase the gain of this, say we go to 1 gig, or 1000 meg, or 10 to the 9th, and we close this, yes, and then we rerun, we see that it goes to -3 now because the op amp didn't have infinite gain. Alright, let's go back and put this back to the way it was, which was 1 meg, MEG. And again, remember, M means milli, so you got to put 1 meg. So we'll hit save, run, just verify it's -2.999 again, etc. On this one, we are doing a DC sweep where we're sweeping the input and then looking at the output. So we're going to get plotting, and our plots on the x-axis is the input, and on the y-axis is the output, and of course the slope of the V in versus V in is 1, that's the green, and the slope of V out versus V in is 2/3, that's the blue. This is a diode showing an active element. If I right-click on the diode, I can look at the characteristics, get a new diode. Here, I've just put in this directory a model that's .model, or I've just put in .model my diode and used all the default values. I sweep my DC input from 0 to 1, and then I look at the voltage across the diode, and I get it turning on at about 0.6 and then going up at some value. And I can then right click in here and then add, I want an RS equal to 0, and let's see, a VJ built in. You have to look at these parameters equal to 1, and then I can resim, and then I get different characteristics presumably, unless I pick the same values as default. DC sims are useful for looking at IV characteristics of active devices. Here I see my bipolar transistor that I've put in, and I'm calling this bipolar my MPN, and again I'm using the default values. This is a little different because I have two loops. I'm sweeping the first one, which is VCE from 0 to 5 volts and 1 milliamp. Then I've got an outer loop where I sweep the base current from 5 microamps to 25 microamps in 5 microamp steps. So what that means is I set this at 5 microamps, and then I change VCE from 0 to 5 volts in small steps. Then I go back and set this to 10 microamps, then I change VCE from 0 to 5 volts in small steps. So when I run the sim, I get all these different. So this would be for 5 microamps base current, this would be for 10 microamps base current, 15 microamps base current, 20, and 25. Okay. So here I'm going to look at a dot transient analysis, and this is just going to be a divider where, not too interesting, where my x-axis is time. And again, if I press Control and the left mouse button, it'll tell me the average value and the RMS value. If I take a look here, I'm doing a sinusoid, and again, you can play with all these or just use them for reference. I can plot all these with the waveforms. I can right-click and I can attach a cursor to these, and then if I move this over, I can take on that and just move the cursor down. I can take and attach cursor 2, right here, and move it over. And I can attach both cursors if I want to, 1 and 2, and then I can move, what's the distance between these 2 points, between here and here? Well, and then it tells me what the distances are. And that's all by right-clicking. I can change the colors if I want to do that, etc. Here's an RC circuit where I've got a sinusoid. Now, a sine is only valid for a transient. It has nothing to do with the AC analysis I'll talk about next. So let me repeat that. A sine source has nothing to do with an AC analysis. In a tran, the x-axis is, in the simulation data, is time. In an AC analysis, the x-axis is frequency. So let's run this. And we can see that, let's remove a trace. We select the window. Let's remove V in. We can come in and then plot V out by, plot V in, add it to there. We could right click on here and go to add plot plane, and then make this plot plane active. Come down here and select V out. We could then make this plot plane, or I guess for what I want to do, I just will delete V out here, and then I can compare the two. I can put the cursors down, etc. Okay, again, transient, sine, time domain on the x-axis like an oscilloscope. Here's another transient analysis, just showing different values. This is an AC analysis. Again, this does nothing for an AC analysis. Instead, we use the AC signal, and we can right-click on this, and we see that the AC amplitude is 1 for an AC analysis. For transient, which we don't have selected, we use the sine source. So we're doing an AC analysis in decades with 100 points from 1 Hz to 10 kilohertz. The x-axis will be frequency. So here I go from 1 Hz to 10 kilohertz. My x-axis is frequency. I can put my cursor down and say, oh, where's 20 Hz? Oh, 20 Hz is right there if I look in the bottom. This signal here is the phase shift corresponding to this side, and you can right click or you can left click over there and don't plot phase or whatever you want to do. You can right click here and set your axis, or left click, set it to linear, and see what it looks like, etc. Again, DC sweep some input. You look at the output operating point, just shows the operating point of the circuit, no plotting. Transient shows x-axis is the time domain. AC analysis shows the x-axis is frequency. Here's another one, but with a pulse in the transient or time domain. And so you can right click on this, click pulse, put your parameters in. When you run, you see there's my input. My output here is the RC-shaped waveform coming in and going back and forth. Again, this is going to be a time domain sim, and I put a pulse in. And you look at another waveform a little further apart. Here, yet another transient running, just showing RCs, different inputs. We don't have to show the falling edge. We can stop the sim before we get to the falling edge. Here's yet another one, just so we can look at delays and, let's do let's attach cursor 1 to the input and move that over to right here. And then let's attach cursor 2 to the output, and let's go to 50%, which is right about there. And I go down here, and the difference between the two is 815 picoseconds. And close that and remove them. Here, one more sim with an RC circuit, but this time using a piecewise linear, where at time 0 I'm at half a volt, at time 3 ns I'm at 1 volt, at time 5 ns I'm at 1 volt, etc. Time 0 I'm at half a volt, at time 3 nanoseconds I'm at 1 volt, at time 5 nanoseconds I'm at 1 volt, at time 5.5 nanoseconds I'm at 0 volts, etc. This is useful for putting arbitrary waveforms into the circuit. Notice if I want to determine the power, the average value of V out, I can press Control and left click, and it says, hey, the average value is 333 millivolts and the RMS value is 496. Here's a switch. When this is a clock pulse, when this is useful for basic circuits, when this pulse, which goes from 0 to -1 to 1 volt, gets above this terminal, which is ground, the switch closes. When this voltage goes below ground, the switch opens. So here I've got a DC source. Let's run the sim. First thing I'm going to plot, I'll just right click on this node. You see that it goes through ground. Let's see if I can put ground on there. Nope. This pulse is set up to go through ground at this time. Closes the switch. When the switch is closed, the 5-volt source is connected to the 1K resistor and the 1 picofarad capacitor, so it behaves just like a pulse source. Here's my switch model. R off, when the switch is open, is essentially infinite. R on is 0.01 ohms. Can't put 0 because you can't have 0 resistance, but it can be very close to 0. You can see the RC time. We can zoom in if we want to. We can fit. We can zoom out. We can fit, etc. Here's another one that's closed circuit, but now notice here in my transient simulation I have used initial conditions. I put an inductor here, and I said my inductor has an initial current of 5 milliamps. Now the way the pulse is set up, it starts at -1, but I've switched the minus and the plus of the switch. So it starts out with the switch being closed. At 2 nanoseconds, the switch opens, but the current wants to continue flowing in the inductor. So initially, this point's going to be at ground. When the switch opens, this is like the current wants to continue flowing in here, so it's going to continue to pull a current through the 1K. So if I pull a current up through the 1K, it's going to cause this potential to go negative. So let's run it. At 2 nanoseconds, the switch opens, and then this current flowing in here, which is 5 volts over 1K, because at DC the inductor is a short to ground, continues flowing, and so I get 5 milliamps flowing in 1K being pulled in this direction, so it goes to -5 volts. Now, if you're looking at this, and especially if you're a grad student or you're taking a course, you've gone through the sophomore circuits and you don't understand these things, it's probably a really good idea to go back and review these first semester circuits or second semester circuits concepts. Here I've put an AC source, except I'm using a linear sweep for my x-axis, and I've got an RLC, and so at low frequencies the inductor shorts the output to ground. At high frequencies the capacitor shorts the output to ground. At the resonant frequency, the energy from the capacitor is transferred and sent over to the energy in the inductor, so they cancel. So it basically just looks like a 1K resistor. These two cancel each other. So I run that, and I see, sure enough, that as I sweep my input at the resonant frequency, roughly 505 megahertz, these two cancel one another, and I get 1 volt times 1K, or 1 amp times 1K, or 60 dB, or 1,000 volts. And let's show that that's 1,000 volts. Let's do linear. Okay, it goes up to 1,000. And of course, the reason you use logarithmic or dB is that allows you to plot big numbers with small numbers on the same plot. Here's an ideal integrator where I've got an AC input, Vn, which is just AC1, and then since I've got a .AC analysis, I'm going to sweep the x-axis with frequency. The x-axis will be frequency, and I get the 1 over F, or 1 over S if you want integration in the frequency domain, the phase shift of 90. Last but not least, I put a pulse in here, and I integrate a pulse. And the pulse, when the pulse goes positive, since it's an inverting integrator, the output integrates down. When the pulse goes negative, the output goes up. Notice how here I put .IC, set the output initially to ground. If you look, it starts at ground. And then run the simulation from 10 microseconds with a 10 millisecond step. Again, you can play with all of these simulations. They're found right here on the video, right next to the video in this zip file, and then the verbal descriptions are here in a PDF. You can back the video up, you can download the video, you can repeat it and keep going through. You can change these net lists, you can experiment till you understand what's going on, and you can do the calculations. Let's stop here.